Well, hello, everybody, and welcome, a very warm welcome to everyone who's joined us for this, the first webinar for 2021 in our Data Science in the News series. And this series is jointly hosted by Queensland Academy of Arts and Science and the Queensland University of Technology Centre for Data Science. So my name's Kerry Mangerson, I'm Professor of Statistics at QUT, and I'm Director of the Centre for Data Science. Even though we're experiencing this meeting online, we're all standing on the lands of Australia's First Nations owners. And I'd like to acknowledge the Turrbal and Yuggera people as the First Nations owners of the lands on which QUT now stands, and pay our respects to the elders past, present and future, their laws, their customs and creation spirits. We recognise that these lands have always been places of teaching, research and learning, and QUT acknowledges the important role that Aboriginal and Torres Strait Islander people play within the QUT community. So what we will do in this panel session is ask each of our 4 experts to give a 5-minute glimpse through a data science lens into the topic of the day, which is the data science of COVID-19 and vaccinations. Very topical for now, and we'd like to know why data science in this, this issue of vaccination for COVID-19. We've got a great lineup of speakers, and while they're speaking in their 5-minute presentations, I'll ask you, the listeners, to use the Q&A channel in the Zoom session to raise other thought-provoking questions. And in the last part of our time together, I'll put these questions to the expert panel and look forward to hearing their insights. If we don't get to all the questions in the time available, then we'll ask the panel members to put some of the discussion around the questions online after the session's completed. So let's get started. I'd like to start by introducing our panel members. And so today we have Dr. Adrienne Jenner. So Adrienne is a lecturer in mathematical oncology at QUT, and she'll be talking about what modelling the immune response to SARS-CoV-2 infections can tell us about COVID-19. So Adrienne Jenner's research focuses on the applications of mathematical modelling in medicine, and for the most part, her research has been in developing mathematical modelling to understand cancer formation and treatment. And so more recently, she's been involved in developing systemic and tissue level models to the immune response for SARS-CoV-2, with the goal of understanding the distinction between severe and mild responses. So our second speaker is Associate Professor Dan Nicolau, and Dan is an ARC, Australian Research Council Future Fellow at QUT. Now, Dan is actually physically right now in University of Oxford, and it's 2 a.m. So great thank you to Dan for being part of this panel. We're really excited to have Dan as part of the panel. He's a QUT mathematician, physician, and ARC Council Future Fellow. He and his team are collaborating with colleagues at the University of Oxford on a UK clinical trial to test common asthma inhalers as a treatment for COVID-19 infection. So our third speaker is Dr. Kirsty Short. Now, Dr. Short is a research fellow and a head of the viral pathogenesis lab at the University of Queensland. And so Kirsty is going to be speaking on COVID-19 a year later. Kirsty, it's great to have Kirsty here from the University of Queensland here in Brisbane. She's an ARC DECRA research fellow, and she has extensive experience in emerging viral pathogens and pandemic preparedness. And she's working on SARS-CoV-2 and in particular the role of children in the disease spread and the impact of this disease on people with diabetes and the development of new antiviral therapies. And our last speaker in the session is Professor Raja Jerdak. And Raja is the Professor of Distributed Systems and has a chair in Applied Data Science at QUT. So Raja is going to be talking about COVID-19 vaccination strategies and importation risks. And so Raja's work on the Disease Networks and Mobility, or DiNeMo project, explores how human infectious disease found overseas might spread in Australia and overseas due to the movement of people, and how this spread can be predicted. And so his main research interest is around dynamic network modelling, and I'm sure he'll tell us a lot about this. Networks and network science are really powerful ways of representing physical and logical relationships to gain insights into a broad range of systems, from communication and cyber-physical systems and Internet of Things to individual and entity relationship networks and interactions to guide value-creating decisions. So this is a great lineup of speakers. And so what I'd like to do then is to start. So what we're going to do is start with our first speaker. Again, we give each speaker about 5 minutes to talk, and we'll start first then with Adrienne Jenner. So over to you, Adrienne.
Thank you very much, Kerry, and thank you everyone for tuning in to listen to my talk and everyone's talk today. I think it's going to be a really fantastic panel. And so probably by now you will have heard of COVID-19 and the pandemic, and the effect it's having on our world is significant and probably won't be able to be actually quantified for many years to come. But it's not just about mask wearing and lockdown and even funny memes. There's a lot more to COVID-19, and there's even some positives that's come out of this pandemic. For example, this has given us the unique ability to bring together doctors, experimentalists, clinicians, and mathematicians right now to develop novel techniques and to help combat this disease. And so from this massive effort throughout the world, we now have not just one clinically approved vaccine, we have 6 approved vaccines, and we have 41 vaccines that are actually in clinical trials. So it's been a huge effort, and there are some positives to what has been a pretty terrible last 15 months. So to start off, I wanted to just start with this question: what is COVID-19? So COVID-19 is the name we give to the disease that's caused by SARS-CoV-2, which is a virus that infects usually through the nose or mouth and enters into the lung. And once it's in the lung, it starts off by infecting cells. And so once it's inside these cells that are in our lungs, it will start to replicate and create usually a few thousand replicants. And then after that time, it will then kill off that cell that it was inside and release all its new viral progeny to then go on and infect neighboring cells. And so our body has a way to combat this, and it's the reason a lot of us might develop asymptomatic disease, and it's because infected cells are able to signal the immune system. And our immune response, once it's been signaled, will come into the lung, wherever the infection might be, or the throat, and start to clear off any infected cells. So how that usually happens is the immune system will start to induce apoptosis in an infected cell, and so that cell will die, and slowly the virus will start to disappear. Now, we know that there's a lot of people who actually develop severe disease and become hospitalized, and that usually is because something goes wrong in this immune signaling. And what ends up happening is the immune system causes damage in healthy parts of the lung or healthy tissue, and causes huge amounts of inflammation that end up causing a lot of diseases or cause a lot of other symptoms in these patients. And fortunately, because this is such a massive pandemic, there's been such a huge effort to understand this question of why do some people develop mild or severe disease. And so as a huge, I guess, worldwide effort, what people have been able to do is collectively come up with 2 main disease correlates, pretty much, and these are highlighted here. And so these are 3 different citations which all say the same thing, but there are many out there with exactly the same data conclusions, which is that in severe patients, we see elevated IL-6, which is a signaling cytokine that helps recruit the immune system. And in severe patients, we see low T cell numbers. So T cells are super important because they come in and they kill off those infected cells. So these are really great conclusions we've been able to draw from data from hospitalized patients. However, they don't tell us why people are predisposed to developing severe disease. They only tell us what their symptoms are once they have the disease. And so what we've been doing is developing a technique called a virtual patient simulation. So we created a mathematical model of the immune response to SARS-CoV-2 based on the clinical data that you saw on the previous slide, and created 200 virtual patients that were all unique, and they were all drawn from the data and the distribution of the data. And we then simulated SARS-CoV-2 infection in them. And in our data, we saw exactly what you see in the hospitalized real patients, which is that as the severity of the disease increases from left to right on this graph, so does the IL-6 concentration, which was that signaling molecule. And also as the severity increases, the T cells decrease. So our cohort was able to recapitulate what was seen in hospitalized patients, which then meant we could extract what the common characteristic, or what the main characteristic is amongst our cohort that drives severe disease. And our conclusion was that it is this monocyte to macrophage differentiation rate. It's basically the rate at which monocytes create new macrophages, which are a type of immune cell. And this has actually been really exciting because we've started talking to people who've said they're actually starting to test for this in patients and see that this correlation does exist with disease severity. And so just to lastly point out how this all leads to vaccination. As we know, there is vaccine rollouts throughout the world, and Australia is starting currently. But where can we go now? We haven't actually quite finished with this disease because there's still major questions, such as how will this vaccine affect SARS-CoV-2 ability to mutate? So as you know, the big UK mutation was a huge deal earlier this year because this mutation allowed the virus to become more infectious. So with the introduction of the vaccine into a population, how will this then aid in the development of more fit mutations that might avoid the vaccine or even be more fatal? And in addition, how does the immune response influence vaccine efficacy? So I talked a lot about how we see a range of disease responses. So a big question is, how will this range of disease responses then translate to a range of responses to the vaccine? And so these are two areas we're currently now using our virtual cohort in to help answer. So I just wanted to say thank you, and I hope that gives you a brief overview of what we've been doing.
Thank you very much, Adrienne. That's fantastic, and what interesting work. Really appreciate it. Thank you. So we're going to go to our next speaker now, which is Dan. And Dan Nicolau, as I said, is in the UK. So he has very helpfully taped his presentation. He's online, and he will be available for the question session. But as a precautionary measure, then we have videotaped his presentation. So we're going to play that now. Dan, do you want to say anything before we start your presentation?
No, just thank you for the invitation. I'm delighted to be here. I hope the audio comes through. If anything goes horribly wrong, I can go through the slides, kind of manually, but I think that the recorded one should be okay.
Okay, perfect. Okay, Joyce, I'll hand it to you. Joyce, we have no sound.
Yeah, that might be a bug in the...
We were just testing this just a little while ago.
Is this better? Again for inviting me to give a short talk. I'm Dan Nicolau. I'm a mathematician and also a medical doctor. I'm in the School of Math Sciences here at QT, and also in the math department at the University of Oxford. And what I would like to tell you about for a few minutes is the work that we've done jointly between QT and Oxford on inhaled steroids for prevention of COVID-19. And for a little bit of history, by now everybody knows this top line, but this novel coronavirus, like all coronaviruses, basically primarily affects the airways. Most of the time as an adult, when you have a cold, it's actually coronavirus, an older strain. This is simply a novel ugly strain giving you a particularly ugly version of a common cold. And it leads to respiratory illness in about 50% of the people who are infected. Out of those, the disease is mild in 80%, resembling a cold, it's severe in 20%, and fatal in something approximating 1%, obviously with large variations between age groups and also subject to comorbidities. And in particular, respiratory comorbidities should, and in most cases do, expose people to much higher risks of hospitalization, needing ventilation, needing intubation, needing ICU care, and indeed death. But we noticed, my colleague at Oxford and I noticed very early on in data from the US, from China, and from elsewhere that there's something really strange going on, despite the WHO and other bodies saying that asthma is a serious risk for people developing COVID in terms of clinical deterioration. Actually, there were virtually no asthmatics needing hospitalization or needing ventilation or ICU care or dying, and also very low numbers of patients with chronic obstructive pulmonary disease. These are older patients, generally former smokers. So they in particular should really have been getting very sick and worked. So we started to wonder, what do these people have in common? That's somehow protecting them from severe COVID-19. And as Sherlock Holmes said, once you've eliminated everything else, whatever remains, however unlikely must be the truth. The only thing that they have in common is that they both tend to use asthma inhalers, and particularly the brown inhaler, the steroid inhalers, the preventer inhalers. So we hypothesized, however strange it may sound, that inhaled steroids that these people are taking for their normal lung disease are serendipitously preventing COVID-19 illness in them, or at least preventing serious illness. A further surprise, I guess, is that inhaled steroids act to tone down the immune system. That's what we use them in asthma, which is an inflammatory condition, to prevent attacks. So why would you want a steroid which turns off the immune system in your lungs? You want your lungs to be fighting infection. So here is a model that we proposed. We think that there are two things going on. Firstly, the virus causes a little bit of vascular damage, but its main avenue of damage is in causing inflammation, and a little bit of inflammation is beneficial. That's why you have it when you have a lung infection. But in a minority of patients, what seems to be happening, sometimes it's referred to as cytokine storm in the media. It's not a particularly accurate clinical term, but basically you get a runaway hyperinflammatory picture, and there's a feedback loop of inflammation, where inflammation begets further inflammation until the patient basically can't breathe anymore. And we know that this happens in other diseases, including acute respiratory distress syndrome, and it also happens in influenza. So it's not particular to COVID-19, but it seems to be particularly prevalent, and for some reason, in some patients, it's activated more than in other respiratory illnesses with COVID-19, and therefore we hypothesized that our inhaled steroids would essentially blockade this process, and that minority of patients would go on to have hyperinflammation. The way I usually think about this is it's like putting a handbrake on a car that's in danger of running away down the hill. It wouldn't stop a car once it's already picked up a lot of speed, because inhaled steroids are like handbrakes and a fairly gentle treatment. But if you put the handbrake on at the top of the hill, then it would just keep the car from rolling down. So we carried out a clinical trial to test it. We used 400 patients in primary care with a symptom and a positive COVID test. They were randomized either to immediate ICS treatment or 28 days of the usual conservative care, and then we followed them up every day for 28 days, comparing how many needed to go to hospital, what their saturations were like, if they had fever, what their heart rate was like, respirate, self-reported symptom questionnaires, and also we measured viral load in blood as well as inflammatory markers. And here are the results. One person was hospitalized in the usual care arm, and one person was hospitalized in the inhaler arm, and 10 people were hospitalized in the normal care non-ICS arm. So on the surface of it, a 90% reduction, which is better than vaccines, than all the vaccines actually, after accounting for the new variants. In the top left-hand panel, blue is the inhaler, and red is the usual care. So you see the probability of clinical recovery in the days, and so you can see people are recovering faster with the inhaler, whether or not they need hospitalization. In the bottom left panel, you see the highest fever recorded on each day. The visual care arm on the left and the SNI arm on the right, and although the distributions are broad, you can see the mean and median are both higher. Basically, people have more fever without the inhaler. In the top right panel, you see basically self-reported. This is how runny is your nose, how coffee is your chest, do you have fever, do you have malaise? It's a combined score. You can see that basically people feel better day by day with the inhaler than the other arm. And in the bottom right panel, it's a little bit more complicated, but a mathematical simulation of our trial basically indicates that in order to get these results, it works out to about a 3,000% reduction per day in needing to be hospitalized, or to say it otherwise, you're 30 times more likely to need hospitalization per day if you are not taking the inhalers. So these results are better than a lot of extremes. And here are some reasons to be excited. Vaccine development has been an amazing effort in the past year. But there are reasons why we don't have vaccines for most viruses, and that's because vaccine efficiency is initially high and then it's undercut by mutations. That's already happened with COVID-19 variants. Vaccines are expensive, and most of the world can't afford to buy them, these new ones. They're difficult to store, they're difficult to transport, they're difficult to deploy. Unfortunately, many people are suspicious of vaccination. That is just a fact of life. And perhaps most importantly, hopefully vaccine efficiency isn't undercut too badly by the mutations, and we end up with something like what we have for influenza, at 70% efficacy yearly. But what are we going to do when the next pandemic comes? These are coming every few years now for various reasons. They're getting worse and more frequent. So we need something for the next one while we figure out what else to do, including developing new vaccines. And the world has billions of asthma inhalers just lying around, costing virtually nothing. And maybe most excitingly for me, there's nothing particular about hyperinflammation in COVID. It happens with lots of infections and other lung diseases, and we've never really understood it. If ICS is like putting a steroid on kind of an angry rash on your skin, then it might work for influenza, which kills lots of people every year, as well as other respiratory bugs, which kill millions of people every year, including kids and babies, and even perhaps something as mundane as the common cold, for which we've never had a treatment. Thanks again, Kerry, for the invitation. I hope this was interesting, and I'll be available for questions.
Thanks very much, Dan. Wow, that's really interesting. Right, so we're going to turn now to Kirsty. So Kirsty Short from the University of Queensland. I'll turn it over to you, Kirsty.
Brilliant, thank you. All right, let me just get my slides up. I was busy listening to the talk and I just kind of didn't pay enough attention. All right, here we go. Everyone can hear me okay? Yep, all right. So unlike everyone else here, I am just a humble virologist. So I'm actually much more comfortable donning on all my respirators and all the containment gear than I am dealing with large data sets. But I think data sets and data has played an incredible role in just how far we've come in this pandemic in the last year. And I just jotted down a whole list of things that we now know a year later that we didn't know at the start of this pandemic, and that's really making a big change in terms of how we manage outbreaks and how we treat and prevent the disease. So one of the things that I want to talk about, because this is our one foray into a bit more epidemiology than lab-based science, is looking at the role of children in disease transmission and really asking, what does that mean for the coming vaccination rollout? So prior to this pandemic, we knew that children played a major role spreading influenza. And so as a result, a lot of people suggested that it was going to be the same for SARS-CoV-2, that children were going to be the drivers of disease transmission in society because children are snotty, they wipe their hands, they wipe them with your face. Anyone with a child or has seen a child can imagine this. And this was actually very controversial. And a lot of people were saying, okay, well, we need to shut down schools, permanently shut down schools. And at that time, we were actually advocating for schools to reopen, especially in Australia. And the reason for that was because we looked at the data and we looked at what the data said. So specifically what we did is we looked at household transmission clusters of SARS-CoV-2. And basically we asked a very simple question. When there was a case of SARS-CoV-2 in the family, how likely was it that it was the child that brought the virus in, and how likely was it that it was the adult that brought the virus in? And we controlled for all sorts of factors like lockdown, school closures, too much to go into here. But the crux of the data comes down to this, that in the 213 household transmission clusters that we looked at, we could only find 8 where the child was the index case, so whether the child actually brought the virus into the family. In all the other cases, it was the adult. And in fact, when we looked at how susceptible children were to infection within the family, children were significantly less likely to acquire the infection than adults. We didn't see a difference between younger and older children, but that was probably because we were a bit underpowered in this. So basically what we saw was that children either didn't get infected or had a rapidly resolved infection, so they weren't bringing it home. And if an adult was the one who brought it home, children in the family either weren't getting infected or they had a rapidly resolved infection. And we're now doing the lab-based studies to understand why. And it seems to be that the innate immune response of the nasal cells in kids is just infinitely better than that of adults. And it can just respond and control the virus much more efficiently. So based on these findings, our sorts of conclusions were things that really were for a while quite controversial. It's much more accepted now, but that children do not drive the transmission of SARS-CoV-2 in the community. And so we really argued that in a lockdown situation, schools should be the last thing to close and the first things to open, in particular primary schools. And this is also taking into account that school closures can have long-term detrimental effects for childhood development. Now, to relate this back to the vaccine rollout, I think a lot of people have been asking, well, why are we vaccinating adults? When is my child going to get vaccinated? And this is complicated by 2 things. First of all, the clinical trials have not yet been performed in children. These are now being performed in children down to the age of 12. And so we can expect some data from that. But the second reason is because when we look at this, when we look at vaccination, we look at who is most at risk. And we know that children are more likely to develop a mild course of disease than adults. So they're not at high risk of severe disease. And we also look at who's likely to transmit the virus in the community. And it's not children who are going to be driving the transmission of this virus. So likely what we'll see is at some point, probably children, say 5 years and older, will start getting vaccinated. But I think people don't need to be concerned at this point in time in the vaccine rollout schedule that we're not looking at children, just because it's just not a priority for the reasons that they're largely protected and that thanks to their immune system, they're largely protecting us from spread. Thank you.
Oh, very interesting. Thank you very much, Kirsty. That's excellent. Okay, so we'll turn now to our last speaker, and that's Raja Jerdak from QUT. I'll hand it to you, Raja.
Thanks, Carrie. All right, so I'll be talking about COVID-19 vaccination strategies and importation risks from a network science perspective. And I'd like to first start off by talking just a bit about the DiNeMo project, which stands for Disease Networks and Mobility. And this project is a collaborative project between CSIRO and QUT, involving all the people you see there on the screen. The idea of the project is looking at people movement as the main driver of the spread of many infectious diseases, and looking at the contacts that are generated by that movement and the disease spread as a diffusion process on top of that network. Now, just as I woke up this morning, I saw this story on BBC News, which actually highlights the scarcity issue current vaccine availability around the world, and actually helps motivate what I'm going to talk about in the next slides. So what we've been looking at is how to select an effective vaccine strategy for COVID-19. And obviously, most countries are prioritizing vulnerable populations, such as the elderly and people with other pre-existing conditions. But in many jurisdictions, there's a limited number of vaccine in that jurisdiction, which begs the question, who should get vaccinated first or next after the vulnerable population is taken care of? And to answer this question, we started looking at different vaccination strategies from two perspectives: the effectiveness, or how much the vaccine is likely to limit the spread by selecting certain people, and how much complexity and cost is involved in collecting data in order to inform that strategy. So ideally, we want to be in this region here, where we have a highly effective vaccination strategy that doesn't cost a lot to collect the data. Now, one possible strategy, and probably the simplest one, is a random vaccination strategy, where essentially you randomly pick within a population segment who gets the vaccination first. And that has really low data collection costs because you don't need to know much about that population. But it also has lower effectiveness, as some of our experiments show. The next vaccination strategy we looked at is called acquaintance-based vaccination. And here, individuals are asked to name a person they met. And by aggregating the data, we look at the individuals who are named the most, and these individuals are prioritized for vaccination. Now, this has higher effectiveness than the random strategy, but it also involves more data collection costs, and there's room for error when people may not necessarily name or remember who they met in the process. Now, the other strategy we looked at was called degree-based, and this one is a more idealized strategy where you know exactly the number of people that any person encounters on a regular basis. And I say idealized because it's typically very hard to get this data for privacy reasons, but also for ensuring the accuracy of that data. Now, there's been some work on COVID contact tracing apps to do this, but the uptake has been relatively low because of the privacy and ethical concerns there. So this sets a good benchmark for effectiveness because it's quite effective, but it's also has high data collection costs. And what we did is we looked at a strategy and proposed a strategy that's called individual movement-based vaccination. And here, rather than collecting information about the degree, the number of contacts that the person has, we look at the types of places they visit and the frequency at which they visit those places. And the idea there is that people who visit busier places, such as central train stations or theaters, might be more risky for spreading the disease. So what we did with this strategy is we looked at different classes of locations, ranging from your home, where you typically meet your immediate family, and all the way to really busy places like educational campuses, airports, and concerts. And based on those classes, you can determine the likelihood of a person to be a higher spreader. And we create sort of a weighted average of the types of places people visit in order to determine who should be prioritized for vaccination based on the risk, transmission risk level. So we did that initially for influenza-like illnesses in the pre-COVID days, but more recently we've looked at how would these strategies look like for COVID, using all the COVID transmission parameters. So we used an empirical mobility data set taken from a city with over 360,000 users. So this was a location-based social media app called Momo that gives us location every 15 minutes, and you can infer contacts of people based on that. And we did trace-based simulations to look at the spread of the disease by seeding or having seed nodes having COVID-19, and then looking at how it spreads in simulation. With no vaccination, this led to about 3,300 cases. And we see that moving from the random strategy all the way to our individual movement-based strategy, there's a significant reduction in the average outbreak size, and that even with a small proportion of the population, around 2% being vaccinated, we achieve very small outbreak sizes with both the degree-based and the individual IMV, given that the degree-based is impractical, whereas the IMV is very practical. We also looked at how different R numbers might affect the spreading potential, and this is to model the appearance of different virus variants. And we also saw that similar results there, with a roughly 6 to 8 times improvement and a reduction in the outbreak size with this IMV strategy over the other practical approaches. So this was about vaccination, and I just want to say a couple of words about COVID importation risk, because as the vaccinations start ramping up, countries like Australia are going to consider when can we open borders or to which countries. So that's what we looked at as well. And just to give you an idea, here Australia started a staged travel bans on different countries around this time last year, starting with a travel ban on China, then Iran, then South Korea and Italy, and then followed by a travel ban on all countries. And what we did is we used arrival card data from the Australian Bureau of Statistics to understand what is the impact on the likely disease importations from these travel bans. And it's important to know that these travel bans were mainly on visitors, whereas citizens and residents were allowed to return to the country. So what we find based on that data is that a lot of the, depending on the country, there's a different proportion of returning visitors or residents. So for instance, for the UK and the US, there was a significant decrease in the expected importations of COVID-19 as a result of the travel ban. And that was because both residents and visitors were less likely to travel to Australia. But interestingly, in countries like Italy, we saw an actual increase in the expected arrivals, because when the travel bans were being announced, there was a sudden rush of citizens to return to Australia, and even their direct family dependents who are not citizens or residents were allowed to return. That's why we see an anomaly there. But just looking at these numbers, and taking a network-based approach where we look at the incidence rate of COVID in a source country, the volume of travel into Australia, and where people go in Australia and to which airports, we looked at estimating the risk of estimated expected importations by country, and that analysis is valid for August 2020, so it might have changed now given the change in incidence rate. But what it looks at is the expected arrivals from a country versus the incidence rate, and it classifies countries according to different risk levels based on that network modeling. And in that instance, countries, some Asian countries actually were quite lower risk because they had lower incidence rate relative to the volume of travel into Australia. And with that, I'll thank Gary, and I'll leave it there. Thank you very much.
Thank you very much, Raja. That's excellent. Right. Well, I couldn't have asked for a better group of presentations, and they were so interesting individually and collectively. They've given us just such a rich picture of this area. We're going to move into some questions Q&A session now, and these questions are open to all of you. So just raise your hand if you'd like to take one of these questions, and we can and then we've also got some questions in the chat which are more directed to an individual, but we can open them to everybody as well. Now we'll have about 20 minutes for this session, so about 15 minutes actually. So we've got lots of time. If you're interested in putting a question up, then please do so. So we'll go to some of the questions that are that have been posed, and this one's actually for, despite what I said about them being open, this one's actually more directed to Adrienne. So Adrienne, the question is, I'd love to hear more details about the distributions for the virtual patients. So what other distributions did you generate, and what methods did you use to generate the distributions?
Yes, this is a really great question. So there's a few different techniques to to create these virtual patients. And so we followed one that had been previously published by another collaborator of ours. But basically what we did was we started off by creating a mathematical model for the immune response to SARS-CoV-2, which is a system of ODEs. And we calibrated many aspects of that model to in vitro data in the literature, so nothing specific to SARS-CoV-2. And then what we did was we took all the hospitalized patient data. So I showed a small subset there, but there's a lot of data on all aspects of the immune response in hospitalized patients. So we took that and we fit our model to the average patient. And then we had the average patient's parameters. And so from that, we could then draw randomly from distributions centered at this average patient parameter to create our virtual cohort. And we chose 10 parameters, which we found were most sensitive in our model. And we chose the standard deviation for those parameters, or the distribution from which to sample those parameters based on the distribution of data for the hospitalized patients. So basically normal distributions with a mean that was obtained from the hospitalized patient data and the standard deviation from the variance of the data. What methods did you use? Oh, so that's basically how we generated our 200 patients. So then we confirmed as well as as a check, which I think is really important in these virtual cohorts. For each patient we created, because they're unique, we simulated the disease course for them, and we just made sure that nothing crazy or out of the realm of reality happened. So for every patient, we checked that their disease course sat within the range that we see for hospitalized patients. So for IL-6, as an example, we know IL-6 might range from 10 picograms per milliliter to 1,000, which is quite a large range, but we made sure that no patient that we had in our cohort exceeded that range. So we just double checked that they were realistic virtual patients.
Okay, oh great, thank you. That's an excellent explanation. So Kirsty, I'm going to turn to you for a question, and then in your study you were looking at children, and one of the questions is around well how old are children, and when do you actually sort of have the threshold for like worrying about children, I guess?
Yeah, so that's something that we looked at, and we know immunologically, children is sort of up to 10 to 12 years. After that, a child's immune system tends to become a bit more adult-like. So I think if we err on the side of caution, we really talk about children as being less than 10 years. Certainly a 17-year-old is not really very different to an 18-year-old. And those sorts of definitions are a bit arbitrary. But we did look at that, and look, it wasn't significant, but again, I think that's because it was underpowered. We did see a trend towards the difference between children under 10 and children over 10.
Okay, oh great. And I'm aware also that UQ was developing a vaccine, and this was a great ambition for UQ. And I know that there's a large department that you're in, and I just want to know, do you have any comments about the vaccine that UQ was developing, and obviously that didn't go forward, but there must have been talk around that, and I know people would be interested in having some insight into that.
Yeah, of course. Look, we were all hoping that vaccine would go forward to phase 3 clinical trials, but the reality of clinical trials is that things drop out along the way. That's why we do them. And I actually think this is a really, really reassuring story, because what it is that the data was looked at objectively, a decision was made, and it wasn't actually, the vaccine looked incredibly safe and incredibly effective. It just interfered with a diagnostic test. But the decision was made not to take it forward. So people should really look at this as reassurance that all the checks and balances that we have in place are not being circumvented because of the pandemic, and that everything and every clinical consequence and every possible complication is taken very seriously. I do know the Q vaccine team very well, and they are now going back and redesigning their technology in the hope that maybe they can help with sort of phase 2, phase 3 rollouts of vaccines, or potentially a little bit what Dan was saying as well, like we need to think about the next pandemic. I know nobody wants to hear about the next pandemic, but the reality is, if you just look at flu, you have a flu pandemic every 30 years. So I know I'm going to get another flu pandemic in my lifetime statistically. Look, there you go. There's my statistics. So we need to think about strategies for those pandemics as well. And these rapid vaccine platforms that are being developed at UQ and elsewhere are ideal for that.
Thank you. That's, as you say, that's very reassuring and a great answer. So we know that there's a number of vaccines now available, and perhaps first to Raja and then to all of you. But how do we sort of better understand the impact of different vaccine features? For example, you know, how the vaccine limits severe disease, the vaccine efficacy, and so on. So how do we understand the impact of that, those different features of vaccines? Can you talk a little bit to that, Raja, and then others might also have some something to say on that.
Sure. Thanks for that question. So for the vaccination strategies, we're learning more every day about some of these features, about their likelihood to limit severe disease and clinical symptoms, and other things about how much they limit transmission. So in our simulation framework, we built it in a flexible way where we can build some of these parameters into the simulation framework and test different scenarios for different vaccines and how they may impact the transmission or likelihood of hospitalization in order to better weigh also how they might interact with some of the vaccination strategies that are being considered.
Okay, great. Does anybody else like to comment on that?
Yeah, I'd like to maybe enter more of a public health kind of messaging, in that I think there's a lot of talk, especially in Australia, about, well, which vaccine should I get? Is the Pfizer vaccine better than the AstraZeneca? If so, why aren't I getting the best vaccine? And I think the message that we really need to get out to everybody is the best vaccine that you can get is the one that you can get. So basically, all of these vaccines do an incredible job at preventing severe disease, so keeping people out of hospital, and that's what we need to do. Some might mean that you get a sniffle versus not getting a sniffle, but we need to focus on the fact that they protect against severe outcomes. So if you are offered a vaccine, take that vaccine.
Okay, great message. Thanks, Kirsty. Right. I want to turn to Dan. And Dan, there's a question in the chat saying, could you please discuss the side effects associated with inhaled steroid exposure in the general population?
Yeah, thanks for the question. Every drug has side effects, but inhaled steroids for asthma have virtually none. These are drugs that have been around since about the Vietnam War. In fact, the two gentlemen who discovered it were interviewed on Swedish TV the other day. They were in their 90s. They were working for the company that ended up getting bought by AstraZeneca. And so, you know, these are very old drugs. There aren't really any side effects, and we're using them for like a couple of weeks, you know. So if you're using them for years at a time, there would be potentially something, but in most countries they're over the counter. So I don't want to say zero. Carrie, as mathematicians, I want to say like epsilon.
Great, we can say epsilon. Yeah, tiny little bit. Okay, so what about more generally then? And this is a question to the panel. More generally, like there's a concern around side effects of vaccines, and we know that there's emerging data about, and obviously a lot of data about the efficacy of vaccines. But would any of you like to address the question of side effects, you know, from a data science perspective or from a virology perspective?
I mean, I can tell you from a virology perspective.
Perfect.
Please don't ever ask me to do stats or anything. So
this is a team effort, Kirsty.
Yeah,
so
exactly. And this is why we collaborate in science.
Exactly. Yeah.
So from a safety perspective, what we've got to remember is that these have all gone through phase 3 clinical trials. And any licensed vaccine, you can be reassured, is safe. No shortcuts were taken, despite the rapidity at which these vaccines were developed. No shortcuts were taken in assessing safety. Some people are concerned about the mRNA vaccines, saying, well, there could be long-term consequences. What if there was a side effect that we didn't see until 6 years from now? We wouldn't know that from the phase 3 clinical trials. And that's true. but I cannot think of any vaccine, any indication or any scientific justification as to why there would be a side effect that popped up 6 years later that we're not seeing now. So as somebody who's in this field, who literally lives and breathes viruses, I have zero concern about the vaccines that have been licensed for clinical use.
Perfect. Thank you, Kirsty. Would anybody else like to say anything to that? Okay. So another question now for Adrienne. Adrienne, one of the questions is there's, and others also will have something to say, perhaps Rajai too. There's a lot of data. There's data from different sources that's being used. So there's challenges around using those various sources of data and integrating them for modelling and prediction and understanding of the disease and also of the vaccinations. Would you like to speak to some of the challenges around integrating those different data sources?
Yeah, sure. I think this is both one of the greatest things about the pandemic is how much data is coming out of it that modelers and data scientists can use, but then also it's a massive challenge to consolidate the data, because you might look at two pieces of literature that are both reporting, say, the IL-6 concentration, and they'll have statistically significantly different ranges. And that makes it really challenging to create a model of the human response. And so a lot of what we've done has been regularly recalibrating our data. Whenever we get a new publication that has novel data, we try and integrate it with the current data that we have. We also have to look at a lot of the time how the experiments are being run and how the testing is being done. Something that up until now we haven't necessarily spent as much time on is how exactly are these experiments being conducted, and is that a reason for the differences in the outcomes when you compare two sets of data? So it's been a really good challenge, and I think we've learned a lot as a modeler myself, and our team has learned a lot about how to integrate different data sources.
Okay, perfect. Raja, would you like to talk to that?
Sure. We certainly encountered similar problems in our area, which is largely looking at different mobility data sets and trying to merge them and fuse them so we get a better picture of the mobility that's driving the transmission of disease among individuals. And some of the issues we face are obviously the spatial and temporal resolution of the data, and which is typically quite heterogeneous from different sources, but also the confidence levels and can we actually trust the source of that's giving us this data, and how can we merge them into some uniform, homogeneous, usable data set. And we actually have a project that's just starting to create a national mobility data asset for Australia that tries to at least provide a starting point for exploring mobility as a driver of future pandemics.
Oh, that's very interesting. And I can imagine there's some challenges there too, not only in integrating the data, but also accessing some of those data as well. Would you like to talk a little bit, Raja, about, I mean, when you're looking at the individual level data here, and of course there's issues of privacy and provenance of data and so on. And health data, of course, is very kept very private. So would you like to talk a little bit about privacy?
Sure. So most of what we've been looking at for the DiNeMo project is spatial temporal data relating to people's location, the sequence of their movements, and all that. And even when anonymized, there are privacy risks with the data. And there's a lot of research that's been done that shows that for some individuals, in fact, for more than 90% of the population, just knowing 4 locations of where they go can provide a nearly unique signature of who that person is. So even with de-anonymized data, but having location data over time, there's a significant chance that people can be de-anonymized. So there is a lot of work also on potentially perturbing the data sets, maintaining the distributions, but hiding some of those features that might help identify people in order to allow research to progress in a privacy-preserving way. And this is an ongoing research challenge that we have to deal with quite often. And you mentioned provenance. So when we do hide some of those features, we still need to ensure that they're still capturing the distributions and that there is a verifiable link to the fact that this data still represents what is happening on the ground empirically, rather than it becoming some theoretical distribution that does not link to reality.
Yeah, thanks, Raja. And I think also a lot of these data are very clearly bound in ethics and access constraints. And so all of us, when we're working with data, are bound by those kinds of rules around how we use those data. So Dan, would you like to speak to that as well? I mean, this is an area of interest for you as well.
Yeah, thank you for the question. You know, you're the expert on data, but I guess one observation I would make is that not enough inspection is done of data. So, you know, they really hammer you about this in medical school. You know, when you go to see like a patient, you always want to barrel in, like start taking blood pressure and bloods and like listening to the percussing the chest. This was always my sin. I was much better at percussing the chest than anything else, so I went for that. And the consultants are always like, stop, what are you doing? Just look at the patient. Like, are they sick? Are they pale? Are they laughing? How are they dressed? Do they smell bad? You know, I think in our rush to compute like eigenspectra and like eigencentrality distributions and stuff, hardly anybody anymore really stops and just like inspects a data set for a while. The whole Stoic study, all of this stuff, you know, I've got an email on my desk from Tony Fauci saying like, how did I miss this? Good question. Why did he miss this actually? And it's because hardly anybody stops to just look at what's there, anonymized, you know? You can look at means, just very simple things, and just kind of get a grip on data before you jump in. I guess that would be my data science comment. About the privacy, well, that's tough. And as Raja said, you know, if you just know a couple of points on geo or where people are buying their meds or even what meds they have, you can kind of like work backwards. And hopefully there are not too many cyber attack groups working on that, but I'm sure there are some. Those are probably things that the world just has to come to grips with. We used to live in villages where everybody knew everything. So maybe we're thinking about privacy kind of like the wrong way. Now that it's all a big village, maybe we should kind of like relax some of our expectations regarding privacy just because the world is what it is.
Yeah, thanks, Dan. And I guess that's, but it also, it's interesting, isn't it? There are these concerns about privacy, and we respect those, but also I think by the contribution of the data, especially as we've seen happening for COVID-19 and for the development of these vaccines, it's really the contribution of the data and also then the aggregation of data from different sources, our ability to be able to do that has really also helped to understand this pandemic, understand then the impact of interventions like vaccines on populations, and helped us to develop this rapid response that we've been able to see for this disease. Yeah. Okay, do you want to speak any more to that then, Dan? Do you want to comment?
I guess just throwing it. I mean, obviously, you know, a rally, a tennis rally between us. But so, you know, what would a person in the public prefer, right? We could either have a situation in which scientists and doctors and nurses and allied physician, you know, professions have used massive amounts of data to mount absolutely historic, you know, response to this thing, in return for some loss of privacy. Would a person in the public prefer for 10 times people to have died in return for like some you know, protection of privacy? Like, you know, it's a loaded question the way I'm saying it, but we got to balance, you know, and as Kirsty was saying, it really has been an amazing response, right? And data has absolutely driven it. There's no doubt about this. By the time my paper appeared, it was cited 13 times, like just as it hit medRxiv. That's, you know, 20 years ago or even 10 years ago, that would have been unimaginable. And that happens with every paper like that. So there has to be at some point some discussion about like, well, you know, we need to like find cures for emergent diseases quickly. And yes, people may have to sacrifice a little bit of privacy. how do we feel about that as a society? And I guess every single society has to kind of have that discussion, but certainly in Western societies, I think most people would agree that, yeah, it's okay to lose a little bit of privacy in return for scientists being able to like get to problems quickly.
Okay, thank you. So that brings us to the topic of a future session in this this panel session. But for now, for this session, it's time to bring it to a close. So the panelists will have a chance to respond to the questions in writing after the seminar, and these will be posted on our website after the recording of this session. Panelists, on behalf of all of our listeners, I want to thank you for your time, your insights, and for your great presentations. Your expertise in this area has really helped us all to understand this a lot better. I'd like to thank the Queensland Academy of the Arts and Sciences, and I'd like to thank the QUT Centre for Data Science for initiating and hosting this seminar series, and a special shout out to our colleague Joyce Wang for technical support and brilliant work behind the scenes. In fact, Joyce is the manager of our Centre for Data Science. She's leaving us on Monday to go for other adventures. We'll be so distraught that she's leaving, but we wish her very well for the future. And we'll certainly be thankful for all the work that she's put into helping us to set up this series. Data Science in the News webinars will be organised from time to time. Please check, they'll be every month now. So for details, check out the QUT Centre for Data Science website, and also follow QUT Data Science on Twitter. Until next time, goodbye and go well.